Okay, I'm not going to go through the list. Okay. Okay, so the lists of our guests are too long to read. I'm going to give you their titles and their names, okay? We have Evan Champagne, who's the architect from Freeman Prince Freeman. We have Dave Duffy, who's the MEP coordinator. Want to be louder? All right. That was a get louder, Rossi. Does anybody have the?
I mean, I don't have.
You guys have mics? Okay, hang on to
I don't
mics.
have one.
I'll just talk loud, like only Rossi can. Evan Champagne. Let's give it up for Evan Champagne. All right, approved. Dave Duffy, MEP coordinator for PC Construction. Jason Peters, virtual construction manager and graduate of Oregon State. Don't tease him about that. And Megan, how do you pronounce your last name?
Levick.
Megan Levick,
Yep.
who's a, what is your virtual construction engineer?
Yeah, yeah,
Wow.
that's right.
Virtual construction engineer.
Come on, louder.
Okay, and I'm going to dim the lights and let you guys take off with it. Sound good?
Sounds good.
Okay. So.
Okay, can everybody hear me?
Yeah.
Good. So I can get things started. Just a little background information on us and some experience. Jason and Megan, and then David, we're all from PC Construction. PC Construction is in Williston, do a lot of work in Vermont. South Burlington, sorry. Tilly Drive, right?
Yeah.
Tilly Drive, South Burlington. Freeman Prince Freeman is in downtown Burlington. Done a lot of work in UVM, Jefferson Hall Rescue Facility. It's still in design, and also the STEM project. And Freeman Prince Freeman. So, does anybody work in BIM now, or taking a class in BIM? A few of you? Great. So, what is BIM? So BIM is a 3D model that also has some non-graphic information with it. So it's a parametric model. You've got elements, 3D elements in your model that also have information associated with it. So the type of material, quantity, the manufacturer, the cost of the material, and you can assign information to it as well. The way we typically work is there's one central file that gets continually updated from the different people that are working on it. And then your local file talks to that central file. So we're all working with the most up-to-date information. And then this document can be transferred from the design team to the construction team, and then ultimately to the owner to be used for maintenance and management, so that it's a living document and can always continually be utilized and be added to and edited, even after the project completion. A couple examples of some elements from Revit, which is what we use at Freeman Prince Freeman. This is a Connier window, which is a manufacturer of this very specific model. And you can get information about the depth of the window, the mullion, even the website, which you can just click on if you want to go get some more data about it. The type of window, model number, manufacturer, and then you can input things like cost and some energy parameters as well, like solar heat gain coefficient would be associated with this. There's a longer list down below. Roof, here's a roof element, so you got in blue is what's being highlighted here. And then so we got a basic roof, insulation on metal deck, and it says what type of membrane is on it, with the thickness, protection board, insulation, vapor barrier, and metal deck. So these 3D elements have all these layers in them as you're drawing and modeling up the building. And then here's a few views just from my desktop. So this is the STEM project. And the way the BIM model works is you build up the 3D model, but you also set up views. So here's a detail view of an interior detail. Here's a 2D view of just some graphic information. And then here's a plan view. So if I move, a wall in the model, then it moves this wall. Add a window, it shows here. If I move something that relates to this detail, it would show up in this detail, and vice versa. So that you're constantly working with this, this live model. And then, the level of development of a model is kind of how much 3D information we put in there and how much effort you put into developing this model. So depending on the project, some smaller projects, you really only utilize the 3D elements to produce some 2D drawings for the contractor to be built. And then others, you build up in 3D and then utilize some of those for renderings or views or design however you want. And then as you move up to this level, which is kind of fully modeled, where you would model furniture, structural steel as it's actually going to be fabricated. STEM was done at this level here. So we have the steel modeled, we have the mechanically systems modeled, we have electrical, but it's not as it's actually going to be installed. The contractor actually, which you'll see a little bit later, builds up their model for the construction aspect. And this is all based on specific to the project and what the owner wants. So if the owner is willing to kind of wants a model to this level of development, there's some more labor involved. And then, the advantages of BIM, a project the size of STEM would take, a team this large of doing drawings. And I actually brought a half-sized set. So this is half-size. I couldn't even really carry the full size over here. Imagine it's twice as long, twice as big. I think it's 800 or 900 pages long, but you're more than welcome to come take a look at this. And then this is half of the spec as well. I think the spec was around 1,800 pages. And all of that information would have had to been hand drafted, 20 years ago, let's say, or 30 years ago. So why BIM? Well, BIM you can use for design, collaboration, visualization with the 3D, cost estimating. All these things can be done kind of in this one model, rather than needing to do several different drawings independently. You can build up the model in 3D during design, and it contributes to the plan drawings and the section drawings. So kind of the multi-purpose aspect of BIM is what makes it so valuable, both for design teams and construction. That as you're designing it, you're also building up your presentation and your marketing and your collaboration. For instance, as you're designing in 3D, if you've got views set up with borders for your presentation, then as you're designing the building, you've already got those views, you just print them out. Same thing for collaboration. If you've got some views with the structure turned on in your MEP, you can just utilize those views to then develop the model. So you're always kind of contributing to other aspects of the project. You're not doing them independently. And then as the design team, what we're really trying to do is hand over a set of information to the contractor so that they can build the project as we intended it and as the owner intends it. So that's the most important aspect of kind of our whole process in delivering a set of information to the contractor. And a little history lesson about, or a little history on how developing a set of instructions started out for construction. This is a site plan with some trees, some landscaping, and then you can see the wall here. And this was back, 1550 BC. Interesting thing about this is the units are in cubits, so it's a length of a forearm. So depending on whose forearm, you might end up with a different size building. Even 3,000 years later, we're still basically using 2D drawings in the same method of just drawing a plan. And then here there's hints at trying to mimic, you know, a 3D view, but still done in a very similar manner. Fast forward to 1930, Empire State Building, a very complicated building, still being drafted in a very similar manner, with the same types of drawings being handed over to the contractor for construction. 1980s, still kind of doing the same type of thing, where we're drafting. And then handing over, you know, a 2D set of drawings to the contractor for construction. This wasn't all bad. It was fun to, you know, play around with some of this stuff. Protractors and the erasers and the triangles. And then CAD drafting started to kind of be more common in the 80s. Still using 2D design though, and printing out a set of drawings. So you're using the computer, but you're still delivering the same type of documents to the contractor. And then early BIM started in the 90s and had a lot of issues. The graphics were really difficult to kind of understand. And also the computer itself just couldn't manage kind of good representation of 3D views, or and the processing power wasn't there for all of this information, both just raw data and graphic information. So it's very cumbersome and not really being used all that much until, you know, the early 2000s, when, you know, you could start to integrate structure and MEP things and the architecture all into one model and navigate it pretty efficiently. So for BIM, we used for STEM, we used 3D BIM models for the architecture, the structure, and then MEP. So we've got plumbing, electrical, HVAC, was all done in BIM. The civil and the landscape were not done in BIM, but everything else was. And then a close-up model. Even the lab furniture was done in BIM as well. And then some other elements that are just more effective to put in 3D. So we've got a lot of elements, architectural elements. You can see some electrical fixtures, receptacles, I mean, all that stuff is in there. So a little bit about the STEM project. It's a 5-story building plus a basement. The lab portion over here has a full penthouse for mechanical with exhaust stacks. Oh, yeah, it's right here too. So this is the lab portion with the bridge here. See the steel for the bridge coming over to Bodie, which is here. And this is a good example of how, you know, we're using the BIM model for kind of presentation drawings. And at the same time, we have this model that has all this other information where you can just isolate the steel in different elements to see how they coordinate together. So the lab wing is 114,000 square feet. It's 192,000 square feet total. Partial basement on the classroom wing. So all of the labs and support spaces are in this wing with a bridge over to Bodie. And then this has a large auditorium here, medium-sized here, and then larger classrooms here, with offices and grad spaces on the upper floors. And the very beginning of the STEM project was actually a renovation, started out as a renovation of the Cook building. And we had set up a 3D model of the existing conditions of the Cook building and identified different types of spaces, color-coded them, and then laid them out on square footages, type of space, and then the types of renovations that would be needed. So how many square footage of floor, ceiling, and all that. And then as we changed the design and adjusted things, all of this information would happen in real time. It was all live. So if you changed the size of the space, it would change here in this information. So we were tracking cost and the program requirements through the early design process. And what we concluded was that it would cost significantly more money to renovate the existing Cook building for lab use than it would be to build, to tear down Cook and build a new lab building. So for the design side of it, you know, you can grab a lot of this we grabbed right off Google Earth and then import it, export it from SketchUp, and then bring it into Revit. And then just build up some of the, like these two buildings we built up a little more because they were more significant, but that we can very early on get an understanding of the site and how the building fits into the site. So here's a view looking at the STEM building and beyond with Old Mill and Williams, I believe. So trying to pick up on the historic character of the building and make sure that the building is not overpowering. And all this stuff was done pretty quickly.
Evan, there's a question?
That last picture, what program did you use to render that? Was it just screenshots taken from, say, SketchUp and then imported into Photoshop to get that final characteristic?
For this one, yes. This stuff, the early stuff was done in SketchUp. And then Photoshop for rendering. Same thing here. So this was to look at, you know, sectional aspects. So once we have the 3D information in there, we can kind of do these section cuts and different views pretty quickly, which is very useful in design and also conveying kind of our ideas to the owners and users of the building. And also, these same views that we used early on in the design process, we also used to present to the city for the permit drawings, and to present to estimators so that they could get a quick understanding of the building. And here's a few more. And these are right out of the contract the set of documents right over there. So we put these right in the documents so that different trades folks on the project and then the contractor can get a really quick kind of idea of what the kind of scope of the building, the scale of the building, the materials, very quickly and get an understanding. And then it helps inform some of these 2D drawings as well, the more traditional drawings. Same thing on the interior. These are just views of the same model. From the interior, we've got, you know, the actual pattern of the tile. We've got the ceiling system. So this is the actual ceiling system that's in the specifications. You just download this from the manufacturer. And then that same information I showed you earlier with like the website and some of that data is all in there for all of these elements. Another shot. This is in that connector between the two of them, cafe, right off the ground floor. And then the lighting as well. So these are custom light fixtures that we got the model from the manufacturer with all the lighting information in there. The amount of lumens and output of the light, how many watts. And then when we do our renderings, the output of this stuff is per the actual fixture being installed. So that this lighting level, it helps us to get an idea of how the lighting levels actually appear when we do our photorealistic renderings. So this is just those fixtures that were used. Accurate scale, accurate representation of material, so that when we present these to the owner, they get an idea of what the space really looks like. And then those same fixtures can be used by the engineer to run their numbers, their calcs, on each space. So we run foot candle calcs on desktops if it's a classroom, or on the floor surface if it's, you know, a larger common area. Here's a larger classroom. In the classroom wing, same thing. Here's the model of the fixture with all of the specific information. So that as we adjust our lighting layout, we're working with our engineers, and all this information can be changed and understood really very rapidly. And then, you know, a final rendering of one of the views with all of these fixtures in them. You know, pretty realistic views of some of the materials here. And along the way as well, you know, we're also looking at using some of the 3D aspects of the project to help coordinate things. So we've got some structure here that's clashing with some piping. And, you know, we just send a snapshot of this, you know, something like this, to our consultants to resolve issues. So we identify a problem where we've got a pipe running into the cabinetry, and then it's also conflicting with a footing down here. So we've got our structural model, we've got our plumbing model, and we've got our architectural. We just screenshot it, circle it in the plan drawing, and send that off, and that's very quickly communicated what the problem is. And then it also identifies a solution. We've got a wall right here with no footing below it. So we just shifted this over to here, and it was a very simple solution. With 2D drawings, that would have been a very tedious task. And then another aspect of the model is we can directly export the 3D information to our consultants for energy analysis. So this is a breakdown of the building based on the different wall types. The different, you know, we got the curtain wall, the storefront, so the glazing type as well. The roof, the two different types of roof. And with all that information, there's the R values, the U values, and for the glazing, the solar heat gain coefficient, how much light it lets in. Same thing with the classroom wing. And then I've got an energy model a little bit further on as well. So they take all that information and use it for their energy model, which I'll show you. But on the energy side, what we do architecturally as well is on tricky details. So this is where the basement kind of goes above grade, which is a real challenge whenever you've got masonry, because you've got your insulation here, and then you've got support for your masonry, and you're trying to bridge that with some kind of insulation to maintain kind of thermal integrity. So we can run a thermal mapping on that detail and shift elements around and see how we can get the best results. And we do this at parapets, at very tricky details. We can zoom in and run this analysis pretty quickly. So here's the output that we get from the energy model from our consultants. So we send them the model with all that R value and that thermal information of our envelope in there. And then they run their own program on it to get an output get energy output on the building. And in this case, this is the baseline for a lab, for a very efficient lab. And then this would be the STEM building. And we started out closer to here. And due to the amount of hoods in the building, I think there's 130 hoods in the building, it's exhausting a lot of air. So what we initially did to try to increase energy efficiency was just add more insulation to the building. And it virtually did nothing. We added like 4 more inches just to see what that threshold was, and it still did not impact this right here, which is heating. What we ended up doing was using a very efficient energy recovery system. It's a convective system. And that ended up, so as it's exhausting air, it grabs energy off that warm air and uses it on the intake air, the cold air. So it recovers some of that heat out of the exhaust that's being basically just discharged to the outside. And that was where we saw a significant increase in energy. And this was all done pretty quickly. We can change these parameters and get the feedback back pretty quickly. And then the whole time that we're kind of exploring and checking out, looking into the energy aspects of the building, looking into the design aspects, the materials, and working through the design with the owner, those views that I had showed you earlier are also being kind of built up. So in the beginning, when you're first designing, there might just be an exterior here. But as you continue to design and put walls in 3D or 2D, it's being built up in all those different views. So all these drawings are also being developed while you're working on these other aspects. So that kind of multitasking aspect is what makes BIM so valuable for the design team. So these details here, if you find, if you're working on these and you want to change them, improve them, they will be changed on the other drawings as well. So that everybody's working with kind of the most up-to-date version of each detail in the model, and you get a more cohesive set of documents at the end. And here's another scale. So on all these different types of drawings, the model's constantly being updated, and all these views get updated. And the 2D drawings are what we end up handing off to the contractor, along with our model. So now I'll let Jason's next, right? Yeah. So now Jason will go into the contractor side of it a little bit.
So PC, we look at BIM pretty much the same way that Freeman French Freeman does, and that's this central source of information that we can leverage in a lot of different ways and use that, use that information in a bunch of different sort of uses, and everybody's using the same information. So let's start with just what's in the center, the BIM. So we'll actually first start with why we use building information modeling. So basically, it's like the measure twice, cut once. It gives us a chance to build this thing virtually many times if we have to get it right, figure out what the issues are going to be. It gives us a chance to think about what the problems are. If we find a problem in the model, we can take some time to really come up with a good answer as opposed to trying to figure out a solution on the fly with a crew full of people waiting. We make fewer mistakes, less rework. It's basically just more efficient. And for us, I guess let's say digitally, not physically, BIM is a bunch of stuff. So as far as models go, we create our own models for our self-perform work. So this would be concrete, process piping on our water treatment plants, topography, civil yard piping. We can use subcontractors' models if they have them available and provide them. We can use supplier models, like structural steel is a good one. In fact, we saw in the previous model up there on that bridge, that was a model from the fabricator. And of course, the architects and engineers. Laser scans, which I'll get into in a minute. And then inside these models is information. So most basically, geometry coordinates, that's just a 3D aspect of the model. And then there's information that's calculated by the model. This would be volumes, bills of materials, that kind of thing. And then information we add to the model. So, scheduling dates, part numbers, things like that. So I'm going to go through examples of all these. I'm going to focus mostly on our water treatment division of work, and we'll finish up with MEP coordination, which will get more deeper into the STEM building next door. So Evan said, communication and visualization is huge. So this is a meeting in, I think it was a hospital in Concord. And they're using the model to talk about some issue that came up. And I think the interesting thing that also ties into what Evan said is there's an iPad. So it's portable. You don't have to carry that thing around all day. Now this one, it's kind of hard to visualize, but this is a section out of probably a water treatment building that's probably 400 feet by 150 feet. This is a 50 by 50 by 25 foot cube of that building. And we did what we call constructability analysis. But we colored each concrete pour a different color so we could start to look at form work and just the sequence of how we were going to put these concrete pours together, which in this case wasn't very simple. Logistics planning. So this is also a visualization tool, I suppose. This was a job actually down in Champlain College here in town. And what's circled is the addition to a project. This was for a proposal we were putting together. And we wanted to be able to show the owner and the community, what the construction, how it's going to affect everybody. And so we just did a series of different angles on this structure. So we've got, you can see how the crane fits into it, the construction fence. There you can see our trailer kind of tucked in between two buildings because there was so little space for us to work in. How the dumpsters were also going to get squeezed back in there. And then we also looked at, on the sidewalks, how students could get in and around the construction site, which is actually pretty similar to over here at STEM. And signage. You know, we looked at how we would sign the construction fencing near the sidewalks so pedestrians knew to cross the street. Existing conditions. So this is where the laser scan I mentioned comes in. So this is a project in Washington, D.C. That's the Potomac River there in the background. Downtown Washington will be up and to the right. And another contractor, Skanska, built a 26 diameter tunnel from this location at this water treatment plant up to the city. And it's about 4 miles long. And our contract is to come in and build a 7-story pump station inside of that shaft. It's basically a 7-story building upside down. So this is an up-close picture of it. And right off the bat, our concern was for each floor that we put in had to hit these pockets. And each of those beam pockets and slab pockets and then wall pockets right here. And we were worried, number one, that they were even in the right place so that we wouldn't have to stop work if they weren't. And then also to make sure our rebar design would fit into that opening. So we laser scanned it. It's a picture on the right, 2 pictures of the laser scanner. It basically, in a nutshell, spins around, sends a laser out, and just like this laser, wherever it hits, it picks up the X and Y and Z location of that point and gives it the same color as in real life. On the left, each of those tags is everywhere we took a scan. So we took 15 or 16 and then blended them together into one, what they call point cloud. So this is just a screenshot of the point cloud. And you can see the crane, there's like 5 or 6 different boom locations of that crane. That's from each scan, picking up that crane in the different locations it was moving. So then, we needed to know what our structure was going to look like. So this is our model of the pump station. And it's right, it's this one right here, this piece. So we modeled it per the plans, and then basically put the two together. So that's the point cloud. It's a 3D model. We can spin it around, navigate through it. And here's our pump station. And then we put the two together, and we're able to analyze everywhere where those two come together, you know, what the situation was. I think it's a little blurry to see. But we were able to, every single one of those pockets, we looked up close, and we ended up having to change the rebar in a couple locations. This one actually looks pretty good. You can see the pocket is bigger than the actual beam in that case, which is a good thing for us. Construction layout. So we have a team of field engineers. They're basically construction surveyors. And their job is to take what we're going to build and go locate it in the field, find out where it is, and stake it. So the old way of doing this work was one of them would take a 2D AutoCAD drawing and add the points that they wanted to go find that day. And that's kind of hard to tell, but it's those colored, kind of rainbowy looking tags that point to corners. So those were all places they wanted to take their surveying equipment out and go find that location. So what they used to do, put it in AutoCAD, they'd export it to a text file, take that text file, save it to a USB drive, walk out in the field, put it in the total station, and then go do their work. And now with BIM, we're able to take the model, put it in the cloud, and then wirelessly that communicates directly to the total station. And what that gives them the ability to do is on the fly, go find any point they want to find. So on the right is the small tablet that they use, and on the left is what they're looking at, or what they can look at. This is actually a floor of the pump station. And the beauty is, well, obviously the workflow is a lot simpler. They don't have to go through thumb drives and all kinds of crazy stuff. And they're able to spin that thing around and find any point. So if a superintendent comes to them at the last minute and says, hey, I need you to go lay out this equipment tab, they can go do it. They don't have to go back to the office and start over. Here's a video of one of our field engineers actually using one of those tablets and finding some points, or setting some points.
Okay guys, so we're gonna start, we're gonna make some layouts for some equipment pads. We're gonna first create the point numbers. We can have the coordinates and all that stuff. We go first to here, come into the menu, you go to create data, and we're gonna create it from model. So hit that. So I can see here
That's
the model.
that model right there.
I can set it here, all the settings. So I'm gonna hit endpoint. I'm gonna put the point number. I know that the next number is gonna be 10.155. The description, I'm gonna put equipment path. And also, I have to put the layer that I want the points. So I'm gonna put it here in home points. I'm gonna put that layer. So now I'm gonna start selecting all the corners for the equipment path. So I'm gonna start hitting the corners. So once I got all the corners, I will hit here and create. And now I have all the corners computed. So I just already create all the points.
So from there, the screen looks like that, and it's kind of like a video game. He can just follow those arrows and go find that spot. I don't know if you noticed, he said he was on point 10,000 and whatever. When that video was made, I think they were on that first level up right there, and they were already at 10,000 some points. So it kind of shows you we're not doing an AutoCAD and thumb drives and all that. Makes a huge, huge difference. So detailing and quantities. This is a lot like what Evan showed with the 2D plans. So we have this model, and say for a concrete floor, we want to get that out to the field to where they can see it and use it. And maybe they don't have an iPad. You know, we're able to take a model. This is a chemical building in another water treatment plant in Virginia. The green is one single pour. We can isolate that pour. There's embeds in it, some anchor bolts and a sleeve or two. I think there's some rebar dowels in it too. Yep. So we can take that that's been coordinated and modeled in 3D and then put it into just a detailed drawing, 2D, something that you can go hand to somebody. I would love someday to have it all be digital, but I don't, we're not there yet. It'll probably be a while before we are. There's a 3D rendering of that exact same pour. So 4D scheduling. So what is 4D? Right, it's the fourth dimension, I guess. 3D plus time calendar. So what we're able to do is take any model and link it directly to a schedule or time and play it as an animation. And this was done as a proposal for a water treatment project down in Alexandria, Virginia. And same thing as the logistics plan. We wanted to show the client kind of the order we would build it, how long it would take, and what it would look like for their site as the time went on. And if you watch as it plays, the time and date down here would be the scheduled time and date for what's happening at that moment. So anything that turns a color is under construction at that moment, or that time, those days, and when it turns back to the standard color, that it's complete. This is kind of a crazy project. There's a big buried pump station, basically, storage area. That's final grade. There's an admin building that was getting built in the background. We even have some logistics items in here with the construction fence and our trailers off to the left, back right there. And we simply just, well, it's probably not so simple, but we do that by taking a standard schedule, and every one of these tasks gets linked to one or more items in the model. And if you set it up correctly, you hit play, it plays your model the way you're going to build it. Machine control. This is pretty new to us, but it's actually been pretty exciting to see it start getting more popular on our sites. So both these pieces of heavy equipment have machine control, and you can tell by the masts with the two GPS heads on it. And the GPS basically tells the equipment where it is in real life. And there's two of them so that it can also pick up the angle, the direction it's facing. And then of course they have a tablet of some kind on the inside so that the operator can use the information. So what we do, this is a water treatment plant in Virginia. We can take either the surface, so you can see we've got the surface modeled with the roads. These are the roads here, there's probably some curb work in there. Or we can take the yard piping that would be under it and load that into the equipment. And if it's a dozer, it actually knows, the blade knows where it needs to be in order to make that grade happen. So if it's a hill and they're grading it, it's going to do it automatically. If it's an excavator, like in this video I'm going to show, it's not quite as sophisticated, but the operator can see exactly where that pipe is in relation to where his bucket is and how deep it is, so he doesn't over dig. We don't even need staking, which is actually is safety too, that we don't have to have people on site when they don't need to be.
Utilizing a simple, easy-to-use operator interface, the HEX system provides the precise bucket and boom position in relation to the actual 3D design files for the project. This means that final slope grade can be completed without stakes right from the cab of your excavator. And because all of this information is available directly within the cab, the operator doesn't have to reference outside stakes or markers. This also keeps workers out of the excavation area, further increasing job site safety.
Saves a lot of labor too. So the arrows here are telling him how much above or below the digital grade that he is, the BIM model. So if it was a pipe trench, he would know left and right if he's in the right spot, up and down, without anybody having to stake it out for him. And with that, I'll turn it over to Megan and Dave.
For laser?
Oh, lasers.
Okay.
No?
Oh, there it is. Old dancing off.
So, MEP coordination, we're going to go through just a brief overview of our process at PC of MEP coordination and some of the advantages of using MEP coordination as a pre-construction tool for a project. To do this, we're going to use the UVM STEM building as an example. And this is just a little overview of the project. Like Evan said, it's 114,000 square feet, 5-story laboratory building, plus the basement. And I'm just going to go through a couple of the major specifications that we were required to do. We were required to do a fully coordinated foundation model, which is what you see down here on the bottom of the slide. Also required to do a full 3D coordination of all the MEP systems, as well as MEP coordination meetings to go over the conflicts with the project team. And ideally, in a perfect world, 3D coordination is supposed to be all finished before anything is built to minimize conflicts during construction. Sometimes that doesn't happen. So how does the model get built virtually? Over here, on the chart that you see are all the systems that need to get modeled in order to have, the finished product. As you can see, there's a lot of different people that are contributing to making that model happen. So I'm just going to show you over here kind of the process that we do to build the model. So this is the foundation model that PC Construction did. And then we get the steel model from the steel manufacturer. And then the architecture model we get from the architect. And then this is the shell of the building. And now that we have that, we can put in all the MEP systems. So lighting, data, electrical, and then plumbing and fire protection get added in. mechanical piping, and then mechanical equipment and HVAC. And as you can see, there's a lot, starting to look pretty full. And then furniture and ceilings are kind of the last thing. And then you end up with the finished product. So I'm just gonna play a little video of like the final product. It might take a second. So PC does or puts all the models together into this model. So we get them from everybody, and then we kind of line them all up and make sure everything's jiving. And sometimes that can be a challenge. And
So, the challenge, on the challenge, on every job. So what is the model used for? So Megan just showed us how we put our model together. We get individual drawings, or we get individual CAD files from our subcontractors, and that's what you saw Megan putting together. We use it as a pre-construction tool to, number one, to be able to visualize the concept of the job. The architect has done a great job putting together a model with the engineer. They've modeled the product. Everybody has a good understanding of what it should look like. We take over, the difference between us building our model and the architect building their model is when a job goes to bid, in a specification, typically the contract will be written to provide multiple suppliers, or to choose from one of 3 suppliers to build your project. So that's why we end up taking over the model on the construction site. So what we're doing is we're actually putting in our real-world equipment, our real-world ductwork or piping. Excuse me. So as a pre-construction tool, it gives us the ability to visualize the completed project on the construction side. It also allows us to identify space constraints within the building. As you can see in the slide, in a STEM building, in a research building like what we have a lot of components, a lot of piping, ductwork, electrical systems that all have to get crammed into a small ceiling space. You're sitting here right now, you look up, you get a nice ceiling tile, projection screens and stuff. But up above that ceiling, there's a lot of stuff that's going up in that ceiling. Ventilation systems, lighting control systems, fire protection systems. So what we're trying to do is make sure that all of those components will fit within the ceiling space. We also try to identify constructability issues. Constructability issues could be trying to fit a piece of equipment into the building. Guess what? Depending on what vendor you select, piece of equipment is going to change shape, going to change size, could change weight. So it gives us the ability to look at a real world condition with the real steel, with the real elevation of the concrete, and know if something's going to fit in the building. We identify no-fly zones. So, UVM has a wonderful staff of engineers and maintenance personnel that have to be able to get in and maintain the system. Well, if we cram everything into the building right on top of each other's system, well, then they don't have the ability to go in and maintain or turn a valve on, turn a valve off, balance the system. So what you can see here, we put a little yellow demarcation that we're showing the owner, guess what? We're thinking about maintenance of maintainability of the system, of the building, once we walk off the job. The last part of it is identifying clashes. And I think the next slide shows or we're going to go into identifying a clash in a minute. Identifying clashes. So as part of the construction team, we have, like we said before, we've got MEP, mechanical, electrical, plumbing, fire protection. We have a whole group of trade contractors that are putting together their models that PC Construction is pulling together. So what we do once a week, we conduct a meeting with the trade contractors to identify any critical conflicts in the model. But clash detection and modeling is a continuous process. It's not just a 1 day a week review of the entire model. Contractors are talking amongst themselves, trying to work through most of their conflicts. Then once a week, we'll go through and we'll wrap up action items from the previous meeting. We'll talk about RFIs and outstanding and new RFIs as we get into the documents, reviewing specifications or the design. We'll see different aspects of how things will get constructed. Well, that'll raise a lot of questions, so we put through an RFI, request for information from the engineer or the architect. So once the RFI is answered, we plug that information into the model, we talk about it. We go through submittal status. A submittal, I don't know if you know what a submittal is, but we have a product that is in the specification from the engineer. So we submit, we pull the vendor's information together, we give it to the engineer for approval. So we'll go through submittal status and talk about what may have or may not have changed in the submittal that you're actually going to purchase rather than the way it was designed. We talk about 3D clash detection. So that, again, that's going through the model and making sure that the electrical conduit isn't running into the mechanical piping. We talk about schedule, sequence of materials, how we're going to build and layer the equipment into the building or the piping or the ductwork. Who needs to go first? What wall needs to go in first? Items to complete for next week. So we'll wrap up the meeting with, you know, a list of clashes or whatever we need to resolve throughout the week, or we might even go out onto the job site to resolve the clash. So here's a sample of a clash detection. This is actually a clash that we had in the STEM building. So right now we've got the pink is a piece of ductwork, the green is some electrical conduit. So we're trying to figure out, well, how do we resolve this clash? So in many instances, it's not just a lopsided or one-sided approach to clash. You just move your pipe. But there's a lot of rules, what we call rules of the road, when we're installing the facilities. For example, drainage piping. Anything that's gravity fed, we typically require a priority of that system, because there's no pressure behind it, so it requires gravity, obviously, to get out of the building. It's pitched pipe. So there's typically only a short avenue to be able to get from point A to point B above a ceiling space. Lighting. Anybody here wants to be a lighting designer? Good, because you guys are the, no, just kidding. Lighting, well, like Evan had showed in one of his previous slides, lighting is very, very particular in any building system, because you can't just randomly put light fixtures in a building and expect to have a good coverage of light. So, you know, there's always a balance of making sure that the light in a room is just right for sleeping or studying, whatever comes first. So we build these priorities into our design process. Again, ductwork. You know, we have a couple of pieces of ductwork, supply air ductwork, that's, I don't know, about 7 feet wide and about 4 feet tall, running right down the middle of the building. Guess what? That's not going to move very easily. So we build these rules of the road into our design process. But again, sometimes it's just not simple to say, move the duct, move the pipe. So as a collaboration, as a team, we say, we'll figure out what's the best process for doing it. And in this example, it was, we moved the conduit down, or we moved the conduit over, gave a different route for it. We ran the ductwork up to clear over top of the conduit and the fire protection pipe, as well as drop the fire protection pipe so it would get under the ductwork as it went out the other side of the building. Oh, sorry. And that's the end of me.
So the coolest part of my job is being able to think about all the other stuff we can do with BIM that we're not currently doing. I picked 4 things that are kind of out there. These are all things that are happening now. It's not crazy, mad science. These are not things we're doing yet, but drones, we've kind of looked into how we can use drones. One of the big troubles there is the FAA, more than anything else, and not getting sued. I think you actually have to have a private pilot's license to fly a drone for a business right now, which is completely crazy. 3D printing of concrete, which is super cool. They're doing it in China at a research university, and they've built a whole concrete house out of a printer. It's amazing. And of course, virtual reality, mixed reality. But I've got a video of a new product that I guess would be considered mixed reality or augmented reality. And it's, I think it actually just came out this week, at least for developers. And this video is more based for architecture, but I could see it working for us equally as well. It's pretty amazing stuff.
Architects are dealing with shapes and spaces and light, and they dream in 3D. And then you need to translate this design into a set of 2D documents. HoloLens present a completely new paradigm. Triple provides design solutions for architects and structural engineers.
Anything that involves getting dirty is our business. Literally hundreds of enterprises can be represented on a job site. Today, the best way those companies have to interact with each other is paper drawings. But people aren't good at visualizing 3D.
Microsoft HoloLens is a head-mounted, self-contained computer that lets you see holograms in the real world.
You get the physical model as a focus point for the team to collaborate around. And you get the hologram with the flexibility, with the ability to run quick iterations.
You'll see how we brought in the courtyard that you suggested. You see that mouse go off the screen and into holographic space, and you're then interacting with the hologram with the mouse.
The thing that we can do for architects is really give them much higher confidence around decision making. One way we can do that is we can allow them to literally immerse themselves in the scene that they're building and see street side how the building's going to look.
Visualizing design data in the context of the real environment is a much better way to make sure the design is implemented correctly on site.
Microsoft HoloLens allows you to collaborate with somebody regardless of distance, like they were there. Hello there.
Hey Igor, where they're trying to put this door, there's a beam behind here.
I'm looking at this beam. We're interacting with it about a problem that we can see and being able to solve that problem with all the data that we need in front of us in real time.
When I'm talking about enterprise construction, I always compare it to people trying to make music together. Each one of them is contributing to the harmony, but they all should be completely synced.
My gray hair says I've been doing this for a while. I've seen a lot of these new things come and go. And I expect in 5 years, we'll all be interacting with the world with this kind of technology.
So I've heard this was actually developed for video game, some sort of video game collaboration plan, I don't know. But it didn't take long for Trimble and the building community to kind of pick up on it and see the value of it. And I don't know, I bet we're using that in 10 years. It's kind of neat stuff. So in closing, whenever I say I do BIM, everybody always says use Revit. Like that's equal. We use tons and tons of stuff on any given day. And I would actually argue that BIM is a process. you know, David always says, whatever he is, that BIM equals teamwork. And it's leveraging information and workflows.